This is Project 7 Applications of the class of Electronics. This is the last video I'll be recording. Turn that down just a little bit more. Alright. This is more or less a continuation of Project 6. For this first circuit here, we have essentially a diode, a continuity detector that can be used for diodes and other such components. You can see here there are slight revisions from what was designed in the lab manual to what I ended up doing, mainly the movement of this 10K resistor. Before it, there should also be a buzzer in parallel here, but I just couldn't draw that in on Tina. All right, what's happening without it was it was just sending power through all the time. So a quick little video of this just to show, this is without any components in, just to show that the thing works with given an open connection. You can see it does. Please let me go on to the next video. Thank you. And here it is tested against multiple components. Head here just a little bit. Catch your mind there just for a second. This LED here is broken, and you can see that by it's not conducting anything, even though it should in that configuration, just to show that it's still working. Then reversed, and it still works just fine. You can see here, diode works that direction, but it will not work in the opposite. And you'll have to trust me that that is the correct lane over there, which you can just see. There it is. Alright, so we put the capacitor in this way, connect it. What happens is the capacitor immediately charges, causes a slight thing to go through, and as soon as it's charged, there's 9 volt voltage to go through. And then in the opposite direction, you can see it is slightly on, and I'm not sure if you can hear that on the video, but there is a slight buzzing noise coming from the buzzer. Let's see. That was just a test I did to make sure that the buzzer wasn't broken. The inductor does just work. As you can see, watch this yellow light here, actually. What had happened here is I put the white cable in the wrong hole. Watch the yellow light here. It's still on, even though the rest of them it all turns off on pretty much. All right, that's enough of that. On to the next thing. The toroid. Basically, the idea of this is you use the toroid to boost the voltage at this point beyond the point which the transistor would turn on, and allow more current to flow through, causing more the LED to experience a higher voltage, which in turns turns it on. Whereas before, if it's just from here to here, it won't turn on because, well, it doesn't have the voltage to reach the turn on point, to turn on of the LED. Go ahead and mute that. You can see here the light is barely on with the system in. And to show here, just to prove it, remove with some components. I believe I haven't done it yet. Removed it, and as soon as I get this thing clipped here, it is not enough, as you can see, to turn on the LED. That is just hooked up straight to the power of the base of the transistor and the LED, which you can see there's the straight power from the power supply is not enough to turn on the LED. Circuit 3 is a cruel mistress. Essentially, the idea is, I believe, that depending on the waveform of the triangle wave and its combination with the other the dimmer circuit to only turn on for certain wavelengths, I believe, is the idea here. I'm not too sure. But I could not get it to work. On the next slide, you will see a video explaining my frustrations that on the night of, after approximately 3 hours of me working on this.
So this is circuit 3 for project 7. As you can see, the LED is not lit up currently. And I don't know if it should be or not, to tell you the truth. Anyway, so we can take you through the circuit real quick. So over here we got our op amp. And so this is output. This is the minus input. This is the positive input. Got the positive input going to capacitor going out. This is a ground for the waveform gen anyway. Then get the focus. This wire here is a positive lead for the oscilloscope. Anyway, up here, pretty simple. Got a two button switch thing down here. This is to the positive rail, negative rail, just up and down the dimmer, as seen in project 6. And we've got our MOSFET here. The way this one works, it's gate, drain, then source. So we got the output of our second op amp here, let's see if I can get it. Our gate, our LED coming from positive rail of 9 volts to our to our drain. Then our source is grounded over here. That's pretty solid. Yeah, let's see. Anyway, just double check, make sure this bucko's in. Anyway, and then for the second op amp, which is this bit down here, get that hair out of there. Got our output going into the negative. Got the triangle wave going to our positive. Output going down to our transistor. And that's pretty much it. This is kind of what I've been playing with the triangle wave. High-low levels set at 0 and 4.5. I'll show you why here in a second. Frequency, this is kind of what I've been playing with, just a little bit, see what it does. It doesn't seem to do much, if I tell the truth. Anyway, so comes with a oscilloscope here. You can see right now that's maximum on the dimmer. Switch is not on. Press hold that. Kind of does a flippy dippy thing. And while I'm holding the button here, it's going to stay at 4.26 volts. When I let it go, it'll drop down to 960 millivolts, 880, somewhere around there. Anyway, let's trigger that so we can get her in. 880 is what it's saying it is. Anyway, still see it's not on. And I'll swap back through it here. It's now back at its high voltage of 4.18 volts, 4.110, trigger it, 4.08. It's not doing anything. Don't know why. From what I can tell, it should be working. The frequency doesn't change anything. It just set how fast this thing it's not even changing much of the duty cycle. Doesn't appear to anyway. Not like from what I can tell. Here I'm changing the frequency here. it's just expanding out the period, which makes sense which makes sense as far as frequency goes, because the frequency shouldn't have any effect on the period itself, or on the duty cycle itself. And even then, I can go down here to high level. I'm changing the high level now. I'm increasing that. I'm increasing the high level down to its maximum, which I guess is 5 volts. I guess as we lower it, it increases the duty cycle. So yeah, as we're lowering the high level voltage here, it's increasing its duty cycle. Well, now that's lower. Let's try it. Hey, that's a little weird. Anyway, click off it, and yeah, it goes back. Channel 2 should be reading the voltage across the our drain source thing, or DS voltage here. So that makes it look all funky at that level of thing. So as you can see, it's gonna do a dippy thing here. So we get back above the thing. It just doesn't want to behave itself, doesn't appear to be. Try low level. Add low, it just kills it. And then we're negative voltage now, and that doesn't really work. See, it even drained that. So put her back up there. So I don't know what's going on with it.
And now that we're back from that, the last circuit we have videos for, which are parts A and B of circuit 4. Here's part A, this is part B. This essentially uses a microphone as a gate source, as a gate to turn on and off the transistor at certain levels, so that the LEDs experience different levels of voltage. We'll also see this in effect. Instead of a microphone here, it will be a audio in source from my laptop, which is the only audio source I can get to work. My phone nor the lab computers would work with this. It's just essentially the same as far as this part of the circuit goes. It's just using audio in to create a voltage here, which cascades through down here, turning on these LEDs as the voltage is high enough on each goes through, and eventually the voltage will be too low to go through the next diode and only go through the LED. I had some issues with that, but we'll get that here in a second. Here is just the microphone. You can see I'm having to blow on. You can see that move a little bit. If I tap on it real hard, you can lights up for a second. Here, blow real hard. You can see that move, and that is the only way I could get that to turn on. I could not get it very sensitive at all. I tried Darlington pairs up here, as you can see. They didn't do much. I later used a trick that would work for this. I just didn't implement it on this, using the op amp seen down here. Here's the audio source in. You look at those the Darlington circuits I used up here, where this is just playing music and it lights up the LEDs. Little old school music right there too. All right, and here is the level light bar. You can see this one's going pretty bright, barely flickering at all on the low end. See System of a Down, which is a very heavy rock type music, just blasting this thing right here. On the oscilloscope, I was getting about 3 millivolts coming into the system. Not 3 millivolts, sorry, 3 volts coming into the system after the gain stage here. I could not get the gain stage, like this, I'm using this as a gain stage. I could not really get it to work as I was assuming it properly would. The voltage divider I set up here between the potentiometer and this 10K resistor wouldn't change the gain whatsoever, no matter what I did. If I pull that out, put that input, just had just didn't matter. It was always, the voltage didn't change coming out of it. I'm just showing you, again, the music's playing, this is what it's doing. But it was enough gain just from the op amp itself to just give it enough to turn on the LEDs. To the next slide. And the last circuit we have here is just a simple voltage divider that we're using here to test voltage divider at different frequencies. So I had it at 1 volt RMS, which is on the, for whatever reason, from what I can tell, it measure all of the signal gens measure from the zero out, which is the ampli, which makes sense. However, when it says V, whenever you try to put in 1 volt peak to peak, it ends up getting you 2 volts peak to peak, which that's another issue. Anyway, so channel 1 here, see 60 hertz at 2 volts, 2.03 volts. We get 0.99 expected voltage, 0.1015, 2.5% error. And the ratio that we're seeing is 48.8%, 49.1%, 48.3% for 1K and 10K respectively. Nothing really seems that strange here. I mean, it's pretty straightforward. That's what you're expecting. V out is equal to V in over R2 plus R1. But when R2 and R1 are the same, you're expected 1/2 of your input voltage. This gets a little funky. The voltage divider breaks down. I believe that this is in part due to the high voltage, the high frequency of the system just blaring back and forth and back and forth, not allowing either the oscilloscope to keep up, because our oscilloscopes are limited in their frequency, so I don't believe it's that low. I really don't believe it's on the oscilloscope. But it may have something to do with the functionality of how resistors work and how they're expected to work. There is some certain point where everything breaks down as far as frequencies go, and I'm sure that part of it is noise due to the wiring in the system that I had, because it wasn't the cleanest system in the world, but it also wasn't the messiest either. There's a lot of factors when you start getting to higher frequencies, this being one of them. And that is the last slide. It's been a fun class. Glad to participate. Have a good Christmas.